we're now briefly going to talk about filters and ripple voltage. And so the basic idea here is that the output from these rectifier circuits that we've considered aren't quite clean enough to power DC devices. So we need to clean it up a bit first before we can plug them in. So of course, our output now, we have something that looks like this more or less. We have rectified our sine waves. So initially maybe we had something that looks like that. But of course, ideally what we want for a DC device is just a constant level. And we're not going to have it exactly constant. We can get close with some techniques we're going to talk about in another class. We're going to talk about switching power supplies and voltage regulators and all of that stuff. But right here what we're going to talk about is just a really simple way to clean this up a little bit. So the simplest thing that we can do is actually just put a capacitor in parallel with our load resistor. So the simplest way to clean up our output is to use what we're going to call a filter capacitor. And we're going to put that in parallel with our load resistor. And so I'm not going to draw a diagram because it's, I think, pretty simple to conceptualize. We just have a resistor and we're going to put a capacitor right next to it, connect it in parallel. So filter capacitor in parallel. And so let's look at sort of what a plot looks like. So here I have a plot, and what I have is basically what our output looks like without the capacitor from a rectifier circuit. So we've rectified it. We no longer have two polarities. We don't have positive and negative. We just have positive, but we want to make this a little cleaner. So let's assume that our capacitor is initially uncharged. So initially, we're going to do another curve here that has, so with a capacitor, and both of these are output voltage. So what we're going to see here then is that if it's initially uncharged, of course it's going to start down here at 0, and then it's going to charge up with this output voltage here. Once it gets to a peak, however, remember our capacitor is going to want to, the voltage can't change instantaneously. It's going to have some time constant that's associated with the circuit, so it's going to decay, the voltages, but not instantly. So what we're going to see is if we size this appropriately, we'll get a curve that looks something like this. So it decays kind of slowly, and then at some point it's going to rejoin this green curve and it's going to begin charging up again. So we're going to get something like this, and then again at the peak it's going to start decaying until it gets to this point, and then it's going to begin charging up again. And of course this should look sort of perfectly cyclical. Everything should be at the same point in terms of the peaks and valleys, but that's just limitations of my drawing ability. Okay, so a couple key things that we want to define about this sort of plot here. So of course we can see if we do sort of a rough sketch, I know it's kind of hard to see if they're overlaid. So now we have gone from sort of our initial sine wave, our AC input, to a rectified output. And now we have gone, if we look at sort of steady state, we have something that looks like this. Let's clean that up a little bit. So we have something that looks a little closer to this as our output. So again, we don't have that perfectly straight line, but what we're going to see in an equation is the bigger we get the capacitor, the closer we can get to that approximation. Okay, so let's go back to defining a couple key things here. So this sort of lowest point we can call a voltage VL to be consistent with the textbook's notation. And note, I've already labeled this VM, which is sort of this maximum point of our peaks. And so the difference between these two is an important parameter called our ripple voltage. So I'm going to define that as V sub R. So let me write that a little better so it doesn't look like a gamma. So V sub R is equal to Vm minus VL, and that is defined as our ripple voltage. And so this is a key parameter when we're talking about the quality of filtering for a rectifier. So ripple voltage. Another important parameter is our ripple frequency, our ripple period, which we can define by going at any point. Again, just to sort of be consistent with the textbook, we can look at sort of these 2 points here. So any sort of going one cycle and returning to the same point by definition is a period, so we can define this then, this distance here, as our ripple period. So I'm going to call that T sub ripple. And we'll talk about the ripple frequency and some equations here in a little bit. So I don't want to go through the derivation, but if you look on page 76 in the textbook, what we can show is that our ripple voltage is approximately equal to our maximum output voltage, V sub m, divided by R, which is our load resistance, times that filter capacitor C, times our ripple frequency, F ripple. And of course, F ripple is just going to be 1 over T ripple. So let's write that explicitly. So our ripple frequency equals 1 over our ripple period. And one thing to note is that that ripple frequency, we're going to have to be careful whether we're talking about a half wave or a full wave rectifier. So for our half wave rectifier, we have that our ripple frequency is just equal to our input frequency. So F ripple equals our input frequency. However, if we're talking about a full wave rectifier, our ripple frequency is actually going to be double our input frequency. So F ripple equals 2Fn. Let's scoot that over and add a 2 here. And so the reason for that is if we look at this picture, of course, think about what our waveform initially looked like. So initially we had something that looked like this. So by bringing this part of our waveform up, now we've essentially doubled the period because we're sort of counting every peak as opposed to just every other one when determining that period. So looking at this equation here, what we can do then is typically we'll know from specifications what our maximum output voltage is and what our resistor value is, our load. So our specifications are going to indicate our maximum voltage for our load and our load resistor. And then typically we're going to have some desired ripple voltage. So maybe for more sensitive equipment, we need to keep that on the order of tens of millivolts. But maybe for less sensitive equipment like lighting or heating, we can have that on the order of several volts. So based on these things, what we can do is we can determine what size capacitor we need. So determine capacitor size needed. Okay. So a couple other expressions that we're not going to derive, but I just want to sort of put them out there. If you want to see more details about the derivation of these equations I'm about to write, you can look on pages 78 to 80 in the textbook. But basically we can also derive some equations for our diode current. So we can say and so I should note too that these following equations are for full wave rectifiers only. And typically that's what we're going to be dealing with. Of course, the added complexity of a diode or 3 diodes isn't going to be too much cost compared to our improvement in efficiency. So the first equation is for our peak diode current. So again, it can be shown, we're not going to, that peak diode current is approximately Vm divided by R. So that's our peak output voltage divided by our load resistor. All of that times the quantity of 1 plus pi times the square root of 2 Vm divided by Vr, where Vr is our ripple voltage. We can also show that our average diode voltage is equal to 1 over pi times the square root of 2 Vr divided by Vm times the quantity of Vm over Vr, Vm divided by R, times 1 plus pi over 2 square root of 2 Vm over Vr. And again, you're not going to be responsible for how to get these equations, but at least be able to know how to plug in values to use these. Again, one important thing to note, the ID peak I think is pretty self-explanatory. That's the maximum diode current. This ID average, however, is the average diode current for the entire cycle. So let me just make this explicit. So this is for the entire cycle. So that's when the diode is conducting as well as when the diode is turned off. So it's not just while the diode is on. So what we're going to do in the next video is look at a design example with a rectifier circuit. And then from there, we're going to move on to talk about some different types of diode circuits.